Okay, we still have one seat here, and one seat here, and one seat here.
This one's broken, this one's broken.
Pardon?
This is broken. No,
No, sit down. Thank you. So we have one seat here and one seat here. Could you guys in the back please move up here? They're the best seats in the house. And there's a seat here that's open too. Great. Now we've got, let me see, one broken seat. So what do you two guys in the back do? Now, somebody have a piece of paper that we can write down where you're at. So this is row one. Start from your left to right. So you're row one, seat one, row one, seat two, row one, seat three, 1, 4, 1, 5, two seat number, one, and so forth. So when the sheet goes around, put your name and put your row number, your seat number in. And we'll do this the same way. And just on the back of the sheet, we'll just put the right side, the left side, row one, seat 1, 2, 3, and so forth. Then when you come back next week, and also on Friday, please try to sit in the same seat. And I'll try to post the seating assignment on the screen so you know where you're at in case you forget. Everybody with me? Super. Does somebody have a piece of paper we can circulate? Great.
I do.
Thank you. Review from last time, we talked about 4 different things we have to look at in this course. The fabrication technology, the CAD tools, the circuit structures and circuit design, and device models. And we said we're going to spend about 4 weeks bouncing back and forth between these 4 areas. Hopefully at the end of that time, this should all come together. So please bear with. I think that will happen. I'd like to make a few comments about some jargon you'll see tossed around. And this has to do with Moore's Law. And this came from Wikipedia in August of 16. And as you're aware, Wikipedia is not stationary. So we keep getting different definitions in Wikipedia. So for Wikipedia, it says the observation was made in 1965 by Gordon Moore, co-founder of Intel, that the number of transistors per square inch on integrated circuits had doubled every year since the integrated circuit was invented. It was invented about 1959, and it took a little while to get into production. So he was making a prediction based upon a really, really short window. In subsequent years, the pace slowed down a bit. Data density has doubled approximately every 18 months, and this is the current definition of Moore's Law, which Moore himself has blessed. Most experts, including Moore himself, expect Moore's Law to hold for at least another 2 decades. That was the view as of 2 years ago. Now, I'm sure if you go online, or if you go to conferences, you'll see a lot of people making statements. Moore's Law is dead. Moore's Law ended 5 years ago. Moore's Law ended 10 years ago, and so forth. Over and over and over again, statements like this are made. Well, first of all, we have to realize Moore's Law is not a law, it's an observation. So the question is, can everybody be right? Well, this is a good way to write articles. People get attention when they write an article making a prediction like this about something which is not rigorously defined. In April of 16, and his position I don't believe has changed, Brian Krzanich, who was the CEO of Intel, basically said that I'm here today to really show you and tell you that Moore's Law is alive and well and flourishing, and consistent with the comments of Moore a year earlier, it made statements he expects to continue for a long time. So when you hear comments about Moore's Law being dead or being not dead, they're probably not particularly important. What is happening, however, is the performance capability of integrated circuits is doubling about every 2 years. And that performance capability may be in the sense of more transistors per unit area, more speed, more computational capabilities, and so forth. The technology is moving along like crazy. Whether the exact specifics of Moore's Law are being satisfied or not is really incidental. Make sense? Okay. Let's talk a little bit about feature size. So here's a top surface view of a transistor. And again, don't worry about where this comes from yet, but in the lab we're going to find that we intersect two polygons together to form a transistor. And the transistor is formed in the intersection of these two polygons. So it's in the purple cross-hatched region right here. And the feature size of a process, which gives us some idea about how big our devices can be or how many we can put on a given integrated circuit, are typically characterized in terms of the minimal lateral dimensions of the transistor. Oftentimes the minimum length or the width of the gate. We'll see those are defined to be the length and the width of the gate respectively. So if we talk about a 1 micron transistor, we're thinking of this dimension and or this dimension being 1 micron. They're usually about the same. Actually, it's oftentimes also the minimum width that we can pattern this polygon or this polygon. So here is the feature size since it's square. We also can look at a bounding region around that transistor. When we build an integrated circuit, we can put a lot of devices down, but we have to electrically isolate them from each other. So we have to allow a little area around the transistors to isolate the devices. Now, when you have to put something all the way around to isolate things, the area that's associated with the surrounding part can oftentimes be bigger than the area of the device you're interested in. So in the homework assignment, we talked about a 10x overhead in area. And that means that the bonding area might be 10 times as big as the area here. Many times it's even a little bit worse than that. It might be up to 100 times as big as the area of the transistor. All that overhead is there just to electrically isolate the devices. So let me try to draw closure to this Moore's Law comments. Moore's Law is an observation, not a physical law, even though it's termed a law. As we just stated, it's oftentimes misinterpreted and it's oftentimes generalized. Many say it's been dead for several years. Many say it'll be going on for another 2 decades. It was not intended ever to be a long-term prophecy about the trends of the semiconductor industry, although it's been happening since the early 1960s. As I said, it's something a reporter can always talk about if they don't have anything else more useful to say. Accompanying the shrinking of feature sizes is driving down the supply voltage we use to power our devices. So this is a plot of the supply voltages that we have been looking at over the last 2 decades. And we see that for digital ICs, the supply voltage has dropped in the 2 decades from about 1.4, 1.5 volts down to 3/4 of a volt in many cases. Now, back at this point in time, there was typically a single supply voltage for larger digital ICs. Now a digital IC might have several supplies. It might have a 1.1, a 1, a 0.9, a 0.8 volt supply, and so forth. We're going to see that the power dissipation is strongly a function of supply voltage. So if you're in situations where you're not speed critical, you will oftentimes be able to drop the supply voltage down a little bit and save a lot of power dissipation. The analog supply voltage is all over the map. In some circuits we have 2.5 volt supplies today. Other people are building useful analog circuits at 1 volt supplies and so forth. So it's somewhat dependent upon process and particular market opportunities. Here's how the gate length has changed. This is kind of consistent with Moore's Law and the doubling. And we see over the last 2 decades, the gate length has dropped from about 120 nanometers to about 10 nanometers in a state-of-the-art process. And these feature sizes will continue to decrease, but whether they'll decrease at this rate in the future or not is not clear. So we have some challenges when we build integrated circuits. One is managing increasing device count. Today we're putting close to 10 billion transistors on some chips. We oftentimes have a short lead time from conception to the marketplace. Our design teams might only have a few months to get a product into the market. Now, it kind of depends on the product you're looking at. I had a former student that worked for a number of years at TI that was doing the logic circuits that control hard disk drives. A new hard disk drive comes out about every 18 months or every 12 months. They had to have a new chipset in there on schedule. They couldn't get the chipset on schedule, so the hard disk drive manufacturer would probably go out of business. So there's incredible pressure to have short lead times and have everything work on first pass. We also have process technology advances. So what a transistor looks like today and what it looked like 5 years ago and what it looked like 10 years ago is definitely not the same, both physically as well as from the viewpoint of its electrical characteristics. The device performance is getting worse. It's getting better in the sense it's smaller, but it's getting worse in the sense that we typically get less gain out of individual transistors. The variability is increasing. So you have two devices that used to match pretty well if you go back 10 years ago. Now you take two devices that are very small, they may not match very well, and that causes some major problems. There's always pressure for cost reduction as well. And finally, power dissipation is a real issue. We talked about the power dissipation in a high-end Intel processor being close to 100 watts. That's a lot of power to put in a very small chip. In fact, that's enough power you could almost use them as heaters. A couple of questions. Is there an end in sight for this change in the technology? Well, as I stated earlier, I don't believe so. But the direction the industry will follow is unknown. But one thing that is a certainty, society will have an incredible appetite for higher performance integrated circuits in the future. But here's the big concern. If some of you in the classroom choose to go into this field, will you become obsolete at mid-career? Thank you very much. I had a student a number of years ago that got a job at Hewlett-Packard. And at that time, he was working on repairing desktop computers. That was before the Apple IIe. And at that time, those computers were costing around $30,000, $35,000. The computers were expensive enough at that time that they could afford to hire engineers to serve as technicians repairing those computers. And the pay was good. And at that time, Hewlett-Packard made the statement, we always protect our employees. And I asked him, I said, are you sure you really want to take a job like that? And he says, no problem, they'll protect me. About 5 years later, he came back to go to graduate school. He got laid off, and there was no other job available in the company. So he became obsolete early in his career because he had a skill set that was no longer valued. Well, that happened to people who are working in this field. Well, I confidently say the answer is no. Engineers trained in this field will naturally evolve to support whatever the microelectronics technology of the future is. Integrated circuit designers now are being trained to efficiently manage enormous levels of complexity. And any evolutionary technology will result in even more levels of complexity. So I can't imagine that you will have a history major or psychology major being able to come in and handle complexity much beyond what we're handling now in an effective way. I think what we're training people to do right now is handle incredible complexity in large teams and make those systems work. That's your skills in this area. Make sense? So the details may change, but the issue of handling complexity won't change. Will engineers trained in this field be doing things the same way as they are now at mid-career? Absolutely not. There will be changes in the technology and the devices and so forth. So one will have to evolve our skills as well. We can also ask the question, what changes can we expect to see beyond the continued geometric growth in complexity? And I don't know what those changes will be. The changes that we will see probably depend upon the creativity of people like you sitting in this room right now. There's a publication called the International Technology Roadmap of Semiconductors. It has a different name now. And experts get together predicting where they see roadblocks down the road, 5 years and 10 years down the road. And these roadblocks they predict are predicted with no known solutions. Ironically, they define the problem, and it's incredible how successful the engineering community has been at solving those problems where there's no known solution right now. Okay, so I don't think anybody knows what direction things are going to head. There will be new Bill Gates and Gordon Moores and Jim Dells that will determine what that direction is. Most integrated circuits, as I stated last time, are comprised of transistors along with a small number of passive components and maybe a few diodes. Does anybody know why we have a small number of passive components, very few resistors, very few capacitors, lots of transistors? Yes?
Because they're way larger than the transistors.
They're way larger than a transistor. So if you want a single 100K resistor, which you may have used in 230, that may have cost 1/3 of a cent, the lowest cost component typically we had in those laboratories. The area that's required to build that 100K resistor might be enough area to put in 10,000 transistors. And most engineers are clever enough to be able to get more performance or more functionality out of 10,000 transistors than they can out of that one resistor. There are a few cases where you just absolutely need that resistor and you bite the bullet, but it's a very valuable resource. Capacitors are probably even worse. If you have a very large capacitor, the area required is extremely large. This course will focus on understanding how transistors operate and how they can be interconnected and possibly combined with a small number of passive components to form useful integrated circuits. I've got a wafer I'm going to pass around right now. And my request is that you use your eyes but not your fingers to look at it. This is an 8-inch wafer. It's a prototype structure. And what you'll notice is there's a repeated pattern on here. Each one of those repeated patterns is what would be called a die if this were broken apart. So this die is pretty big. The die are about a square inch on this wafer. This was not a production wafer. It was a wafer that was used for testing a whole bunch of different circuits. So there are op amps on here, probably data converters on here and so forth in those die locations. That's an 8-inch wafer. We'll talk about wafer size a little bit later as well. When it gets to that, could you bring it back to me? Thank you. I'd like to talk a little bit about wire sizes for electrical interconnects. If you look at the electric range in your apartment or your house, outside the back of the electric range is a cable like this. And in that cable, there are 3 wires. And those wires are just about as big around as my little finger. Their 6-gauge wiring is typical. It's a 50 amp cord, and the copper wire diameter is 0.162 inches. That's a big wire. If you look at the wires that are interconnected to the integrated circuit, and on that wafer I'm passing around, we've got to make connections to the integrated circuit either with wires or bumps. Those wires are typically either gold or aluminum, and they're usually about 25 microns in diameter. So the wires that we use to connect to the integrated circuit are a lot smaller than the wires that we use for the range in an apartment. How much current is flowing into a high-end Intel processor? How much current flows into high-end Intel processor? Let's assume the voltage is 1 volt and the power dissipation is 100 watts. What's the current going to be? What's the current going to be? What? 100 amps?
You said it was 100 watts?
Yeah. 100 watts, 1 volt, 100 amps, you're right. So we're putting more current into that processor than you put into the range to cook your pizza. We have this tiny wire that's so small you can hardly see it. And it has, if there was one, it would have more current than you put in this wire. So what do you think you do? Can you make a connection with one wire? No, we have to put several wires in, but not too many. So we run a lot of current through these small wires. Don't run them very far, but a lot of current in. Does anybody have any idea why this feature size hasn't changed? The wire. You go back 30 years and the gold wire was still about 25 microns. It's about 25 microns today. And I don't see any, when wire is used for an interconnect, I don't see a likely change in the wire size in the next decade either. Anybody have any idea why the wire size hasn't changed? We'd certainly like to scale this down too. Yes?
And that's the limitations, I guess.
What?
That's to hold so much amperage, and if you keep making it smaller, it's going to burn out.
So that would be one issue. If we made them smaller, we'd have to put more in parallel. So that's one issue. Probably a bigger issue than that. Yes?
Concerned about breaks, fragility.
Yeah. If you look at a wire that's 25 microns in diameter, it's it doesn't have much strength to it. And if you try to make that smaller, we don't have good ways to physically move those wires around. So that's a good observation. The mechanical strength of gold has not changed in 30 years, and it won't change in the next 10 years. Is there a lot of expense associated with putting gold wires in? Gold's expensive, right? Oh, this is oftentimes gold plated too. So you put gold wire on top of a gold pad. Well, there's some expense associated with it, but the wires are so small, the amount of gold in a lot of ICs is still very small. Here's a comparison of analog IC suppliers. We could do a similar thing with digital ICs. If you go back to in 2014, so it's a couple years old, the ranks haven't changed. Texas Instruments, who a lot of people from this department have worked for in the past, Texas Instrument has about 20% of the market share. Their next closest competitor, ST, has about 6%. So it's like an elephant in a whole bunch of much smaller companies in the business. But the ironic thing is, if you go back about 5 years earlier and plotted the rankings, a little more than 5 years, go back to 10 years earlier, ST was number 1, Philips was number 2, National was number 3, Motorola was number 4, and TI was number 5. So we've had a major shift in the key players in this business. Actually, some of these companies no longer exist. Philips has been combined a couple times and no longer exists as Philips. National is now combined with TI. Motorola is combined with Philips, and they're called NXP, and they're in the process of being combined with Qualcomm. So there's also been a lot of consolidation in the industry. I'd like to look at a few people that have played a role in this field. This is the past CEO of TI. I put his picture here because in the mid-50s, he sat in the same classroom you guys are sitting in and went through the ranks and led TI for a number of years. TI is the largest analog semiconductor company. It's the largest DSP signal company. It ranks 7th in the world in semiconductor sales, so a pretty big operation. About 30,000 employees. Sales, about 13 billion. Income, about 3 billion. Is their margin pretty high? 13 billion, and they want to make 3 billion out of that 13 billion sales. That's typical of semiconductor industry. They like to have a big margin on their products. Average annual sales per employee, you take the number of employees, divide by the sales, close to $500,000 of sales per employee. That's not just per engineer, it's for every employee in the company. The average earnings per employee, so if you work for a company like TI, they expect to make about $100,000 on your efforts. Here's another guy that has some ties to Iowa. This is Bob Noyce. Bob Noyce grew up in Newton, and he got his bachelor's degree from Grinnell in 1949. He happens to be the co-founder of a couple of companies, Intel and Fairchild. He's one of the godfathers in this business. Intel has about 110,000 employees, sales of about 50 or 60 billion dollars. They're the world's largest producer of semiconductors. I think they still are. Samsung is pressing them. Average annual sales per employee is very similar to what TI had. Average earnings per employee is very similar to what TI had. Cihat Siddhartha was sitting in this classroom in the early 80s. And he was a co-founder, along with his brother and his wife, of a company called Marvell. They have about 7,000 employees. Their sales, of course, are somewhat smaller because they're a much smaller company at the current time. Average sales per employee is very good at about $500,000 per employee. In 2015, their earnings per employee was not quite as high as some other companies. In contrast to Intel and TI, Marvell is a fabless semiconductor company. They don't have any factory to make their parts. They contract with an external foundry to do all their production. Almost all semiconductor companies that have been formed in the last 10 or 15 years are fabless. The cost of building a state-of-the-art fab is such that it's next to impossible for a circuit design company to be able to afford building a fab today. In fact, most companies that have fabs are turning them into legacy fabs. They will use them until the equipment becomes obsolete, and then most of them will probably eventually become fabless as well. That's three people from Iowa State that played a pretty key role in the business. There are quite a few others. I'll pick one more. Tunç Toluca got a BS degree in 1979. He's currently the sitting CEO of Maxim. Maxim was founded in 1983. So 4 years after he got his degree, Maxim was founded, and he joined the company about a year later. So he joined it when it was a real small company. They have about 9,000 employees, about $2.5 billion of sales, and so forth. In a lot of courses, we don't spend time talking about economics. In this course, we do. I think integrated circuit design is fun. There's a lot of neat things we can do with it. It's also very expensive. So almost everything we do, we only do if we have a chance to make money. So our goal in this business is to grow resources through the development of this technology. Many designs cost tens of millions of dollars. Pretty expensive to design a circuit. Mask sets, we'll talk about the mask sets later, and production of a new circuit are approaching $2 million. So once you have your circuit designed, you need to go and fabricate a series of masks to pattern the features. There's about $2 million tied up in the masks. New foundries costs are around $10 billion. There's not many companies that can afford that kind of an investment. If you look at that, that's over half the annual sales of a company like TI. TI hasn't introduced a state-of-the-art new fab in 10 years, and they probably won't either. Once you get to the point where the annual sales of a company are approaching the cost of a fab, it's kind of like playing a poker game. They all fold. Many companies now contract fabrication, as I said, fabless semiconductor companies. Time to market is usually critical. A single design error can cause months of delay and will require a new mask set. In some cases, a single design error will cause a project to get canceled. Got a large number of people working on a project for a long time, make a design error. They said it's going to be another 4 months till we can get this thing into production. And the client says, we're going to go someplace else. The potential rewards, however, in the semiconductor industry are still very high. So I mentioned Seat Sutard a bit ago. If you look at the Fortune 500 list, he's one of the people on the Fortune 500 list. Did I say that right? They have a list of people in Forbes that were the richest people under the age of 40 or something a few years ago. His younger brother was on that list. So the rewards that people have derived recently in this business have been large, and they will still continue to be large. I think it's important to understand the big picture. We can easily get buried in nitty-gritty details of what's going on, but the important thing is to understand how this technology fits into products and the product opportunities. And to whatever extent possible, I will try to do that. Solving design problems can be challenging. A lot of these designs that require 2 or 3 years and maybe a couple hundred people work on the design, there's hard stuff that has to be done there. So it's really important that you're solving the right problem. Solving the wrong problem is oftentimes just as harder than solving the right problem. So we might ask the question, how can complex circuits with a very large number of transistors be efficiently designed with low probability of error? Could be 200 engineers working on a design for 3 years. Can't tolerate a single error. Can't be an error in communication, can't be an error in concept. No errors. So let me ask the question. How many components were typical of the lab experience that you guys had in 201 or 230? How many components?
10 maybe.
10? That'd be a big circuit, wouldn't it? A lot of your circuits probably had more like 2 or 3 components. An op amp and a couple resistors, and right? So up to 10, very seldom more than 10, usually a lot less than 10. Has anyone ever made an error in the laboratory in these courses? A wrong circuit, an incomplete understanding, wrong wiring, wrong component values, imprecise communication between you and the TA or your partner, frustration with things not working like you want them to work. That ever happened? How often did it happen in every lab? If none of these issues came up, how long would it take to do the labs in 201 or 230?
10 minutes.
You're faster than that wiring, probably 10 or 15 minutes if you had none of these issues come up. So when I've been in the lab, usually when I'm in the lab and in business with some people, they're stuck on something. The circuit doesn't work, it's often has a wiring error or a conceptual problem. So we find it, we fix it, and we go on, right? If you're building an IC, how many of these errors do you tolerate? 0. 0 over 3 years, maybe. With a couple hundred people maybe working on the project. Whoa, is that a daunting task? Going from the case where most people in the room admitted to occasionally making an error in the laboratory. It's not bad. We expect that to happen in 201, and we expect that to happen in 230. But we don't expect that to happen if you go into this business. That's scary, isn't it? How popular will you be if you're the one that made an error on a project that's got 200 people that worked for 3 years? You'll get noted, right? Oh. So let's consider an extremely complicated circuit. By the way, these circuits are much more complicated than the circuits you worked on in 201 and 230 as well, with the requirement to do things that have never done before. So you're trying to build a circuit that performs a way that nobody's ever been able to make it perform before, with devices that are not completely understood. We have new transistors, and we don't have the model quite perfect yet on the transistors. That require several billion transistors. That require 200 or more engineers working for a long period of time, with company investments of tens of millions of dollars or more. Expectation, nobody makes an error. Is this a challenging problem? This is a real challenging problem. So, how do we do it? I'm convinced that anybody in the room can contribute on a team like this if we look at how it's approached. So we have an organizational structure that allows us to circumvent these problems in almost all cases. So we use CAD tools and CAD tool environment to build ICs today. And we're starting to look at some of those CAD tools in the laboratory. There's a small number of CAD tool vendors. Cadence is the biggest player in the United States, maybe in the world. Those are called industrial grade tools, and that's exactly what we use in the laboratory. CAD tool sets help engineers, and it is highly unlikely that CAD tools replace the design engineer. You know, there's always some concern if you automate something, will you eliminate your job? The answer is no. Opportunities will come and surpass what you're doing in the past. So I'll spend just a bit talking about the CAD tool flow. This slide is probably sufficient to show what goes on. We start with system description, we do a circuit design, we do simulation, we do layout. After we do layout, we will go back and extract parasitics from the circuit, and then we'll create a schematic from the circuit that we designed. And then we compare the simulation results of that circuit that we designed with the system requirements. And only if the circuit we designed meets the system requirements do we fabricate the circuit. So we have a feedback loop set up here to make that happen. On the digital community, we do things about the same, except we start with a Verilog or HDL description of the system, and then we typically synthesize the logic rather than do the logic by hand. We'll stop here. Are there any questions? That's all we thank you.
I have a question.
Yes.
I'm interested in various area and
Yes.
I may start